Great. Thanks everybody for joining us today for this webinar on Dyad Studio. Dyad is a new modeling and simulation product coming out of JuliaHub, and we in fact just released the Dyad Studio VS Code extension today, along with the documentation. So we'll walk through a ton of that today. But your main presenter today is Dr. Michael Tiller, who's our Senior Director of Product Management for Dyad. Um, Dr. Tiller is a well-known modeling and simulation engineer and visionary, and he's one of the contributors to the Modelica modeling language. He is the creator of Modelica University and is the author of two books, including Modelica by Example, and he has more than 25 years of expertise at industry-leading organizations like the Ford Motor Company and Ricardo Simulation. Um, he he recently joined us last year as our modeling and simulation director, and will go through how to install, how to use Dyad Studio, and how exactly it's different from the rest of the modeling and simulation landscape today. So with that, I will hand it over to Dr. Michael Tiller.
Okay, thanks, Ranjan. Hopefully everybody can hear me okay. And hopefully everybody can see my screen. I've got my presentation up here. You should see something that's a window that says Dyad Studio Webinar.
Yeah.
So, there'll be a couple topics we'll talk about today: modeling, simulation, scientific machine learning, and ultimately, this all has applications for digital twins. And we'll talk about how we view these different topics in sort of the modern era. And I'll talk about how that comes into play as we go through the slides. So if you have questions, you can feel free to post them in the chat. I'm not going to be really paying so close attention to that, but Ranjan will attempt to answer those questions. And if anything doesn't get answered over the course of the presentation, then you can just feel free to, we'll go through it again, maybe at the end. There'll be some time for questions, I hope. So as Ranjan mentioned, Dyad Studio was released today. I'll repeat that probably a couple times during the presentation. So that's a nice coincidence. This webinar was planned actually well in advance, but it's nice that we timed it this way. So in terms of the agenda for the webinar, I'm going to start by talking about our vision for the product. And then I'll have a discussion of a bunch of topics I think are probably on most people's minds, which is how does this compare, to other approaches to doing modeling and simulation? And that'll be composed of sort of two parts. One will be where I think we've been able to leverage modern technologies in this tool chain, and then another one will be how we think about using and leveraging models. And both of these things are going to play off of quite heavily the underpinnings of Dyad, which is effectively the Julia language. And we'll explain how Julia fits into all of this as we go through this. And then at the end, I'll go through some of the conclusions from the talk. And as I said, hopefully we'll have some time for questions once we're all done with that. So we'll start with this product overview. And a thing I want to point out here is we're trying to weigh sort of the modern technology landscape and state-of-the-art simulation techniques along with things that are happening in the context of product development in industry, and from that trying to formulate a vision for how to move forward, right? What are the best kinds of tools we're going to need moving forward to help people in industry solve their problems. So that's kind of the focus of this section. And the first thing I want to start off with is the name, because it turns out the name isn't just a name we just picked at random. This name really resonated with us because of the things that we see going on in industry. So you may be aware that previously we had referred to the technologies that we were developing under the name JuliaSim, and we decided we're going to change that. So if you've heard about JuliaSim in the past, that is essentially what we're talking about today, but we have a new name for it, and that name is Dyad. So that it's not just the name. We now, as we mentioned before, have this first release of Dyad Studio that comes out today, 0.5.1. Dyad Studio is an extension to Visual Studio Code. So if you go and open up Visual Studio Code and go into the extensions area, you should be able to find Dyad Studio in there and install it. And Dyad Studio is really just the tip of the iceberg in this case. It's just the stuff that we were able to sort of prepare first of the different things that we're working on. So another thing that is in the pipeline is something called Dyad Builder, which is a graphical user interface for interacting with Dyad. And there's also going to be a Dyad command line interface, which we use extensively internally at JuliaHub, and we'll figure out a way to bundle that up so people can use that as well. And that's very useful in things like CI/CD pipelines and just automation and so on. So let's talk about the name Dyad for a little bit so you can understand why we really felt this name resonated. So if you look up the definition of Dyad, the first definition that you come across is, well, at least depending on where you look, of course, but the first definition I came across was the one shown here, which is something that consists of two elements or parts. And it was funny because in looking at the way that people in industry are using tools and approaching modeling and simulation, we kept seeing a repeated pattern of having to balance two things. And so when this Dyad name came out, when we considered it, we thought, wow, that actually kind of captures the spirit of what we're trying to do. So looking at the way people develop products today, we kept seeing this same sort of dyadic nature, and often in the form of a sort of tension between competing interests. So on the one hand, we see a lot the notion of doing engineering in the traditional sense of mechanical engineering, electrical engineering, that kind of work, electronic circuit design or powertrain design, those kinds of things, along with software, because software is just, as Mark Andreessen once famously said, eating the world. It's just, it's getting into everything. And so we want tools that appreciate the fact that modern software or modern product development involves both these aspects and integrating them together. Similarly, and kind of related to the first one, what you see is that engineers oftentimes, and engineering work products are often tend to be very graphical and diagram or schematic centric. Whereas a lot of the tools that people typically use for coding are sort of textual in nature. You have VS Code, you have Git, so the command lines, things like that. And so how can we balance those two things? The need to be able to, on the one hand, look at a system or a product in a graphical form, but at the same time manipulate it in some textual way. Another very common tension that you see now in products is this idea of sort of first principles physics versus data-driven things. Obviously, with in the last year, the last 5 years or so, the sort of AI revolution that's going on, that we're all in the midst of, data, just collecting data and using it and extrapolating from it and recognizing patterns in it has been a huge theme. But at the same time, physics didn't go away. First principles physics are still there. They still work. They're actually still quite effective. And so how can we pair together first principles understanding with a lot of data-driven approaches that are emerging now? And then finally, in terms of modeling and simulation and analysis, there's you can model things in a continuous way, like ordinary differential equations, in a continuous but event-driven way where you have some discontinuities during a simulation and events happening during a simulation. But there's sort of the other end of the spectrum, which is if you want to embed models in software, you have to sort of fundamentally discretize them. If you want to capture behaviors of things like state machines and so on, and then implement them in code, you have to sort of have a representation that's inherently discrete. And how do we balance those? We want to have physics and continuous behavior, but we want to be able to represent it also in the context of state machines and embedded systems, and be able to target embedded systems. And how do we balance those things as well? So those are just some examples of where we just kept running into this idea that we have to find a balance between two things. So let's look at the engineering versus software thing in a little bit more detail, although I touched on some of these points already. Obviously, products are becoming increasingly digital, and the process of developing those products is sort of increasingly involving, I don't want to say two camps because it makes it seem adversarial, but different approaches, let's say. So you have this, as I referred to earlier, sort of traditional engineering work versus more common software and modern software development. And so for many companies, this basically boils down to looking at it in two different ways. And I'm generalizing a bit, but on the engineering side, you oftentimes you find yourself working with schematics or 3D renderings of things, drawings. You are probably accustomed to working with desktop tools and maybe web-based applications, but typically things with a graphic user interface that guide you through navigating sort of the domain that you're working on. The engineering workflow oftentimes is a sort of engineer in the loop kind of workflow. So the engineers are driving it. They are deciding what changes they want to make, and they're triggering the analyses, and they're reviewing the results. So it's maybe manual workflow isn't quite the right term, but this idea that there's a sort of engineer in the loop. It's not an automated process. It requires engineers to make judgments and decisions and take actions. And then you have a lot of times for product development, you have something that's either directly inspired by the system engineering V or similar methodologies where you have a cascading of requirements, and you have sort of a design and a verification side, and maybe even design verification and operations side of the whole product development lifecycle. And that's kind of the way you view it. On the software side, it tends to be quite different, especially if you come from a pure software background where you're not integrating with an engineering workflow as well. You're used to working with source code, you're used to working with source code management systems, you're used to working with integrated development environments and text editors and things like that. You typically have a process where your work is deployed through some kind of continuous integration and continuous deployment process, which ultimately sort of fits into the software development lifecycle of collecting some requirements, implementing code, writing tests, verifying, and then collecting more requirements, writing more code, integrating tests, verifying, and just looping around and around, and sort of taking in requirements as they come. In some sense, that's part of where the agile sort of approach comes in. You don't just sort of exhaustively engineer the whole system, but sort of iterate. So how do we reconcile this is an example of where we have sort of different ways of thinking and acting and working on either side of this, and how do we reconcile these? So our fundamental sort of approach with respect to all of these dyadic sort of aspects of product development is to ask the question, why not both? Why can't we really support both of these sides, so that however you're coming into this process and whatever role you're playing, that you have tools that fit what you'd like to be able to do. So there are a few caveats I'd like to introduce at this point, just to manage some expectations. The first one is that there are a lot of existing tools out there for doing modeling and simulation, and we're by no means making any sort of bombastic statements here that what we're releasing today is going to supplant all those tools that are out there. We're really just getting started. A lot of the other competing tools have had a big head start, and we're trying to carve out some interesting applications where we think we have an advantage, and then take it from there and try and build out from there and see how much of a foothold we can get with our capabilities. One of the things that comes with trying to adopt more modern methodologies and technologies is you can't fully exploit those without adapting to them. And so one of the things to keep in mind is that although some of the ideas we may be and sort of processes that we may be proposing as part of this Dyad platform, they may seem unusual, sort of you're not accustomed to them, but we're trying our best to make it so that they are familiar to people. But in some cases, adopting new technologies, new processes, and new ways of thinking about things is just going to involve some degree of changing from the sort of the traditional ways of doing stuff. So we've mentioned a couple times, today is our first release, which is Dyad Studio, and we will be working on GUI capabilities and other related tooling, cloud computing opportunities, and so on as time goes on. So another caveat is that the future is hard to predict, and we we feel like we've done a good job of surveying the current technology landscape, but it's really hard to predict what's going to happen next. Now, one thing to keep in mind here is that tools that are sort of attempting such an ambitious vision don't come along every day. And so we're trying to come out with a new generation of tools that we feel represent the kind of modern technology stacks that people need in order to engineer products. We'll see where all of that goes, but one thing we want to make clear is that we want people's feedback on these things. I think if you are in this space and you are a user of the kinds of tools that we're talking about today, just keep in mind, this is an opportunity for you as well to sort of help shape the future so the tools of the future will work, the way you would like them to work. And again, you don't get that opportunity every day because although there are a lot of established players in this space, it's very difficult for them to sort of change direction or adapt. Whereas for us, because we're early on in this, where we may be lacking in some capabilities, I feel like we can make up for in the sense that we still have a lot of latitude to adapt our tools. And one thing I will call out with respect to Dyad Studio is that we have a philosophy in Dyad Studio of trying to provide integrated into the Dyad Studio extension immediate feedback to users on whether their units are consistent, whether they're using variables that haven't been referenced, whether their metadata is legal or not, syntax errors, those kinds of things. We want to immediately give you feedback. We've built a platform where I think we can do a lot of that, but we don't actually do everything we can yet. So just be aware there's a lot that the tools are capable of yet, but the implementations haven't been put in there. But I just want to point out that I feel the architecture of the whole thing is actually quite solid as a foundation to build on. And we will get to some of these other things as we go. Okay. So that's sort of the section on the product overview and the way we think about how to harmonize with current product development processes. So now I'm going to talk about the actual approach to doing modeling, simulation, and analysis, and some of the things that we feel from a modern perspective needed to change in the way that we do this. Now I'm going to use Modelica as a reference. We could just as easily do references to other commercial tools. Modelica is a nice reference because it's an open standard, and it's if we make comparisons directly to tools, we have to worry about our competitors getting upset about that, and lawyers and whatnot. So I'm going to sort of stick with just comparing to Modelica. Hopefully, when I show, people can kind of extrapolate to other potential tools. But Modelica is just an easy reference to compare against. And so we'll talk about modernizing. So let's go through this. So one thing to keep in mind about Modelica is it was developed 30 years ago. In the intro, Ranjan pointed out that I was quite involved in the Modelica effort, and I take a lot of pride in that work, and I have huge respect for a lot of the people involved in that space. I want to make it clear that every decision is a decision in the context of the time it was made, and I want to be clear that I'm not trying to imply that anything that was done with respect to the design of Modelica was wrong. If it was, part of that is on me anyway. It's just that times change and contexts change, and it's useful to reevaluate those things as time goes on. So none of this is really a direct criticism of Modelica. It's just pointing out some of the differences that things have changed over time. So I'm going to go through each of these in detail, but I'm just going to sort of bullet point these right now. When Modelica was developed, there was no ubiquitous standard for structured vector graphics. There was really no standard for structured data. There was XML, and it's leveraged to some extent, but not anything that corresponds really to JSON in the modern era. And I'll talk about more of all these in detail. Modelica has this mixture of declarative and imperative code. You write your stuff in Modelica, which is largely declarative. Sometimes you can write imperative code in Modelica as functions. Sometimes you have to write imperative code as C code and then link that in through external, stuff, external functions. So it's kind of a mix. The documentation, the target for documentation in Modelica was HTML, which is at the time very forward-looking. But we'll comment on that on our approach. Handling of media models was something that came sort of later in the design of Modelica, and specifically in the Modelica standard library. There are some language features that support modeling of fluids and media that had to be added. And then the same is really true of state machines. Those also came after the initial design. One of the advantages that we have is that we can sort of try and fit those things in our initial attempt, or at least our vision and our architecture for these things from the start. And Modelica focuses largely on equations and connections, and to some extent state transitions. We're going to add a few more sort of things to that list in our discussion. And a big thing is Modelica really, when it's, in 1995, there was no package manager for the language. In fact, in 1995, I'm not sure there were really very many standard package managers. Now, a package manager is just a given for any new language, that there has to be some way of stating what the dependencies are and downloading them and installing them and updating them and so on. Sadly, even to date, Modelica really doesn't have a standard package manager. I've made several attempts to create one, but they never really gotten a whole lot of traction for whatever reason. So now I'm going to go through these in detail and talk about how Modelica contrasts with our approach. So in terms of structured vector graphics, I think it's, the thing about SVG itself now, I mean, in this case, I'm specifically talking about SVG, the standard, is that it's available everywhere. And that's great. It's available from web browsers. It's available, just everywhere. You can render SVGs to images. You can render SVGs in web browsers. You can render them in Visual Studio Code. Everybody kind of knows how to interpret and render SVG. So that's great. That wasn't always the case, obviously, but since 2011, there's been this W3C standard for version 1.1 of SVG. Lots of tools support it. It's capable of a lot of things. I included this drawing on the side here just to show an example. This is SVG being rendered. It's not a raster image of SVG. It is actually SVG, and it's rendered just fine by the browser, as you can see. And it's capable of all kinds of things. And this is barely even touching on things like shading and clipping, and I mean, it's just, there's tons of things you can do with SVG. So we don't deal with any kind of graphical representations in Dyad. We just use SVG. Another thing to talk about is structured data. So now in Modelica, you have annotations. And I think the idea of using annotations was quite ahead of its time. Obviously, it's used for the graphics in Modelica, and it's used for the documentation and a little bit for experimentation. But it could be used for a lot of things. It allows embedding, for example, customer-specific data right in the models, so that you can associate that directly with your models. Part numbers or experimental setups or whatever. My experience is that it didn't really catch on, in part because in order for anybody who's not a Modelica tool vendor to use it, you had to have like a Modelica parser that you could then where you could interact with the source code. You could read it, you could manipulate it, you could write it. And it just seems like the tools really didn't make that so easy. In contrast, in the Dyad language, we don't actually have our own annotation syntax. We actually use JSON. So it's just JSON that's embedded directly in models. And so it's a very familiar syntax for people to understand. But another thing that makes this particularly powerful is that the Dyad toolchain actually uses JSON as well for its abstract syntax tree representation in all of its tools. So this isn't a feature that we add for customers. This is actually intrinsic to our toolchain, that we do this internally. And one of the consequences of that is it makes it very easy to do what we call lossless round tripping. You can convert Dyad source code into a fully JSON representation where for example, the JSON metadata is represented as part of the larger abstract syntax tree. You can then manipulate that thing. So for example, you can take a given Dyad entity, a definition, a declaration, metadata, write that out as JSON. The tools already do that. What I'm saying is our tools already support that. For example, our forthcoming command line tooling will allow you to do this. Then you can use pretty much any language on the planet, and even some specialized JSON related querying and transformation tools to take that JSON and do something with it. Either read the metadata out of it or inject metadata into it, or perform some transformation on the component. And then you can then feed that back into our tooling and convert it back into Dyad. So that way you don't need a special parser. Everything gets generated as JSON. You can then manipulate that JSON and then convert it back into Dyad losslessly. So we think that's a little bit different than the way that Modelica has done things. And by capitalizing on using JSON, we basically made the representation of the models accessible for every language. And of course, the best language would be Julia. Now, in Modelica, obviously, Modelica has functions. There's a restricted class called function, and you could write functions. Fairly limited imperative expressiveness in Modelica, but of course, if you want more, you can go to C for the complex stuff. Dyad as a language focuses only on declarative constructs. And so the question is then, well, how do you express any sort of computation that that involves more than just a simple expression? And the answer is you use Julia for this. And I'll have a diagram later on that's going to go into more detail about this. But we've used Julia for all the imperative stuff. And this is actually quite neat. And I'll show an example here in just 1 second. Julia features a function. One of the sort of claims to fame is this notion that it supports multiple dispatch. And that is really nice in the context of using it as a way of representing mathematical functions. So I'll give you an example. This is how you could define a simple Julia function. Now, this one's trivial. It just adds 2 numbers, right? So it's not, but you could write obviously more complicated functions. This multiple dispatch, I'm just going to try and show very in a quick demo. If I write such a function in Julia and I say I want to add 5 and 3, it's going to give me 8, right? Because it knows how to do adding over integers, but it also knows how to add. This plus thing is also defined. It can handle dispatches on floats and other things. Now, let's say I bring in the symbolics package in Julia and I declare 2 variables, x and y. What that means is I still have the same function. I didn't have to redefine my add function at all. It's the same function. But because the plus operator can dispatch on symbols, just like it can dispatch on numbers, if I say add x comma y, it gives me back the expression x plus y, right? It doesn't evaluate it. It actually just constructs a symbolic expression for x plus y. And why this matters is that if you want to call out to a function like add from the Dyad language, it may be that we need to evaluate it with actual numbers, in which case it will work. Or it may be that we actually want to pass in some symbols before we do the symbolic manipulation to understand, okay, what are the relationships between these variables? Is what kinds of sub-expressions come out of this, and how would we calculate the derivatives of that function with respect to the first argument, and so on. And we can get that by basically passing in symbols and then getting back the symbolic representation. So this is quite different than, say, trying to call a C function, because you can't get this. If somebody writes a function in C, we can't trace through with symbols and understand what that function is actually doing, but we can do this in Julia. So the idea here is if you pass in values, you get a value back. If you pass in symbols, you get a symbolic expression back. And generally, this means that, there are caveats here, but generally, there isn't a need to be able to specify derivatives, for example, because we can compute them just by looking at the expression. All right. And it's also quite nice because you can develop all of these functions completely outside of modeling and simulation. You can just develop them as normal functions. You can test them, work with them interactively in a REPL. You could plot them, all that stuff very easily. And you can develop a sort of comprehensive library of functions and test them before you actually use them and incorporate them into the modeling. So you don't have this extra layer of modeling and developing models in your way while you're just trying to sort out the mathematical relationships. And it's quite nice because you can write this as just Julia code. And you don't have to worry about whether you're running on Windows or whether you're running on Linux and what kind of processor you're running on and how big an integer is and that kind of stuff. All right. So now I'm going to change topics and talk about documentation. So in the Modelica world, documentation is handled by embedding it in an annotation. And this is, there's a real example from the Modelica Standard Library of some documentation. And again, in 1995, this is actually a very forward-looking view of things, to have HTML and to be able to generate HTML. And to this day, most Modelica tools actually do a really nice job of generating nice documentation that's very easy to browse and has hyperlinks and all that stuff. So this isn't really a criticism per se, but the thing is, in practice, writing embedded HTML is a little bit of work. It's a little bit hard to visualize because all the square braces and getting matching, elements and closing tags and all that stuff. So we've taken a slightly different approach. In 2025, Markdown is really the king for these kinds of things. Almost everything is using Markdown. So we've changed things around a little bit. So this is what the same documentation would look like in Dyad. And so we have this notion of doc strings, which I'll talk about a little bit more. But basically, these aren't exactly comments. These are like descriptive strings in Modelica, those strings that follow things in Modelica, but they always come before the thing that you're describing. And this is all basically Markdown with inline math. So you can see, how to italicize things, how to bold things. You can make bulleted lists. You can like this. You can do math. You can use, mathematical symbols. So in general, it's just more readable than the embedded HTML. So as I said, we replaced Modelica's descriptive strings with this notion of doc strings. So they're used to document basically everything. I showed an example of writing a doc string before a component definition. We can write doc strings before parameters, before equations. So they serve the same role that they do in Modelica to be able to associate some documentation, some description with each entity. But of course, they come before those things. They're also interpreted as Markdown. That means you can do inline images, you can do, as I said, bulleted lists, all the things you can do Markdown, you can do. And those are then easily rendered in pretty much any environment. They support embedded LaTeX. They come before the thing that they're documenting. And I think this is quite nice because that's kind of a natural place for them. Having them in annotations inside of a model or at the end of a line always puts them kind of to the side. This puts them right there alongside the thing that they're describing. We also support multiple lines, which is really useful, as I showed in the previous sort of screen. Having multiple lines allows you to write more extensive documentation, but we follow the sort of git commit convention. So you would write one line and then a blank line, and then you write more detailed documentation. And we distinguish between that first line, which we treat as a sort of short summary of the thing, and then the rest of it, which is the detailed description. There's lots of context in which it's useful to be able to do this. And when we do documentation generation, it's nice to be able to extract a summary. When we do things like tooltips and you're mousing over things, it's nice to be able to have a summary and then maybe more, be able to click and get more detailed information. So, so that's why we adopted the same approach as the git commit convention. This blank line after the first line thing. So you could see that here. This is actually generated documentation for Dyad models. So you can see, I'll kind of start at the bottom here. You can see this is the source code. This is the Dyad source code. You see it's all nicely syntax highlighted. We are using, we have a text-mate grammar for Dyad that you can use in VS Code or with other tools like the Documenter, which we're using here to do syntax highlighting. So that's quite nice. The descriptions that you see on the parameters like spring constant, unstretched spring angle, and so on, they show up here when we look at the parameters, spring constant, unstretched spring angle. We have the units in here, default values in here, the description of the thing, links to, things it extends from. The equations, what's kind of interesting here is that these equations, in fact, none of this documentation is really written by the person who developed the model except this textual description and these textual descriptions. Everything else is just sort of inferred. And so, for example, here, you don't have to write these equations. Those equations are in your model. We're just surfacing them here by extracting the LaTeX and rendering it. But anyway, this is the documentation, as I mentioned, and it's going to improve. This is just the first cut at it, but we're quite pleased with even the first cut of this stuff. So that's documentation, and now I have to do a little trick here to get off of this page because that's an actual web page. Just a sec. Okay. Now, another topic is how media models are handled in Modelica. So this is an example of a Modelica model. It's got a bunch of components in it. It's got two, pipes and valves and sources and so on. And so in Modelica, you would normally, when you if you wanted to create a model like this, you'd create the model, but you'd also have to associate a particular media model with it. And so that involves creating In order to bootstrap that process, you have to create an abstract fluid package that contains a bunch of functions inside of it. And then you would need to go through and decide what functions you needed. So Modelica Media and Modelica Fluid largely do this for you. And so they have this sort of exhaustive set of properties that are used by the components in Modelica Fluid. Then you need, if you want to add a new kind of fluid to work with, you'd have to go through and implement that concrete package representing that fluid, and then override all of the different functions in there to provide implementations of the different property calculations that are needed. And then you would need to propagate all of that down through all of this. So what that means is, in practice, you might have some kind of medium at the top level, but then you have to go through in each component and override the package that it uses for computing properties in each component. And then each of those components has to do that in their component, in the components inside of them, and so on. And that propagates it all the way down the tree. The interesting thing to note about that is, in Modelica, the connections themselves are ignored in this process. So the connections are meaningful in a physical sense, that they, for example, conserve mass, or they have essentially a sort of common pressure amongst the various connectors in the connection set, and so on. But in terms of the actual propagation of what the specified media is, or medium is, that's connections don't play a role in that. In Dyad, we approach this differently. So in Dyad, first of all, we have this concept of a path variable on a fluid connector. And a path variable, the basic idea is that across a flow path, this particular variable, all the connectors in a flow path will have the same value for this variable. So it's not equations that are involved here. It's just, it's sort of saying that there's an alias. Each variable on that path is going to be the same. And you can, typically for a fluid model, what you would then do is make that path variable the medium that you're interested in. It turns out path variables can be used for other things, but in this context, we'll just talk about it for the medium itself. And so in each component, you use Julia's multiple dispatch to compute the properties that you needed. In each concrete medium model, you would go through and you'd implement the functions that you need, but only the functions used by your system. So you don't have to come up with a big giant union of all possible properties that might be used at any point in the future up front. Instead, you can just implement the properties that you need as you go. And these path variables are automatically inferred via connections. So the idea is that if there's a path variable on here that says there's a particular medium associated with this connector, then we automatically can infer it's the same as this one and this one. And then internal to a component, you can actually express this thing called a continuity statement. It's kind of like a connect statement, but it's not as powerful. All it says is that these two connectors are on the same path, and therefore we can infer that the path variables are the same from this connector to this connector. And then again, the connection says we can infer that these are the same, and then the continuity statement says these are the same, and so on and so on. And we can basically build up this whole graph and infer what the properties are everywhere. And then at some point at the top level, you just have to initialize this by connecting a particular medium anywhere in that circuit, and that'll suffice to specify what the value that should be used by all of them is. Okay, in Dyad, we also have state machines. There's a lot of things that Modelica got right in terms of both hybrid system modeling and modeling of discrete systems and synchronous systems. One of the things that we do differently is we have state machines as kind of first class constructs. So, we want to avoid trying to model things as complex collections of when clauses where you can't reason about what states are reachable. We also wanted to have them be more first class so that you don't have to use sort of complex inner outer relationships in order to model states through a hierarchy. So states will be a first class element in our component models. So that's what Dyad will do differently. There's nothing to show here yet. I'm just pointing out that this is something that we've had in the design from the outset. We also, we don't talk in Dyad about equations, we talk about relations, because there's just so many now. It's not just, even in Modelica, when you show like a connect statement in an equation section, people go, that's not an equation. Yeah, it's a relation. It's a relationship between the connectors. And so we generalize this. So we have equations, we have connections. We also have switch statements. We have this, I mentioned before, the idea of expressing continuity, the path continuity through a connector or through a component. We have a connect statement, but it allows you to connect multiple connectors, and the metadata supports junctions in a sort of first class way. We have looping, assertions. So the idea is we didn't want to limit ourselves to just thinking of everything as just strictly as an equation. So you'll see that in Dyad code that it says relations. Modelica has no standard package manager, as I mentioned before, but Dyad, luckily, leverages Julia's existing package manager. It has an absolutely minimal base library, unlike in Modelica, where the standard library is really quite monolithic. We have units and basic connectors in the standard library, and that's pretty much it. And those are all sort of auto imported into every module or every package that you build. This really supports a modular design where you can have all the electrical stuff in one library, all the mechanical stuff in a separate library, and only state a dependency and download them when you need them, as opposed to having a big monolithic library. And another thing that the Julia Package Manager enables is to have a collection of libraries that are out in the public, open source libraries or standard libraries, and then another collection that sits on another server that is private to your enterprise, for example. And so you can build your projects out of a mixture of those two, and it makes it very easy to do. And this integrates quite nicely with both Dyad and with Julia, and pulling in Dyad dependencies and Julia dependencies. And what that means is you have access to the entire Julia ecosystem of packages for doing a wide variety of things. Oops, this slide's a little little messed up in its animation. But in addition, you have this sort of powerful symbolic capabilities in Julia itself. In a normal Modelica tool, you sort of put in Modelica code and you get out either an executable, an FMU, or some C code. And there's really not anything that's going on in between. In our sort of view of this, you want to be able to get in and actually work with a symbolic representation as well. So we have, as I mentioned before, multiple dispatch, which allows you to write functions that can work both symbolically and numerically. That then supports automatic differentiation. We have symbolic manipulation that we do via modeling toolkit, and we give you symbolic representations of that. And we'll talk about that more in a second with analyses. And we have this ability to interact with symbolic representations. So you can drop down into the Julia REPL itself, load your model in as a symbolic representation, and then work on it. And what that allows us to do is to actually create what we call custom analyses, which I'll have a whole little aside on here in a second. But then also just keeping in mind the fact that we have at our disposal the Julia language itself brings in, actually this was supposed to be GPU support, not GPS support. GPU support, just-in-time compilation of functions so that they run really fast, a huge ecosystem of technical computing and SciML packages. Okay, so let's talk about this custom analysis thing, because this is another thing that's really exciting about being able to bind this stuff to Julia. So the value of building models for modeling simulation is to be able to do a bunch of things. One is identify any errors in a design, for example, to reduce the development time, to be able to quickly come up with product improvement ideas and evaluate them, to even extend the use of models into the operations of your product in the field and be able to build digital twins of them for predictive maintenance and asset management and so on. And I came up with this visualization of this, trying to explain how this all comes together. So this column here, the left column, is the declarative part. And this is really the Dyad language. And I'll talk about this column in a second, but I just want to explain the lay of the land here. This is the declarative Dyad stuff. This is the imperative stuff, which means the Julia stuff. And we can divide that further along another dimension, which is when we're talking about modeling. And modeling here is the mathematical description of your problem, right? Expressing your problem in Dyad. So you build models of tanks and resistors and so on in this space. This is the Dyad language being applied to modeling. And then down here, we have analysis itself. So this is actually asking a question about that model and getting an answer is the analysis part. In most Modelica tools, it's assumed that you can run, for example, a transient analysis, and maybe you can linearize something, and maybe you can do a parameter sweep, but there's not a huge emphasis on the analysis part, and it's definitely not extensible. But in our case, this is extensible. What that means is that we have the ability to have somebody build a model up here, describe the sort of all the entities and their relationships and connect them up here, describe the mathematical relationships, for example, the fluid properties here, and then pass us that symbolic representation and do something with it. So we might run a transient analysis, we might run a steady state analysis, we might linearize it. But the point is, because we have this step where we can get access to the symbolic representation, there's a whole bunch of things we can do, and it's extensible. And we use the Julia language to implement those things. So we have a way of describing what an analysis is and how we want to use it over here. And then we have a way of implementing the actual analysis in the Julia side. So we end up with this sort of 4-quadrant view of modeling and analysis. And it just demonstrates sort of the nice complementary relationship between Julia for the imperative side and Dyad for the declarative side. So here's a sort of an example. Let's say that our tools didn't include any kind of transient analysis. Now they do, but let's say they didn't. You could then define a new analysis type. You can say, okay, whenever we extend from this built-in type analysis, we're defining a new analysis type. I'm creating something called transient analysis. It has some parameters. It wants to know what algorithm I want to use to perform the integration, numerical integration. It wants to know the start time, the stop time, the absolute tolerances, and the relative tolerances. And it wants to know what model I'm trying to simulate. So this is actually how we do it. So in other words, I'm not showing you some example, really. I'm showing you actually how transient analysis is implemented in our tool. And once you have that, then you can say, well, I want to create a specialized analysis that is a transient analysis that runs for 10 seconds, that runs my hello model and with the following parameters. And those parameters in the model can be bound to parameters in the analysis. So this is kind of like an experiment annotation in Modelica, but on steroids. And the idea is that you now have knobs you can turn in your experiment, and you can define what those are. And furthermore, you can use the inheritance mechanism not just to extend from some analysis that's been defined in a library, but you can then extend it further from there and say, okay, well, I want to extend from the world analysis and create this world 2 analysis where at least the default ambient temperature is 200 degrees Kelvin. So, very similar to Modelica, but now we're not talking about the model itself. We're talking about what we actually want to do with the model. And then you can write Julia code that will be essentially executed in all of these cases. So you write Julia code for this part right here, and then each of these will then in turn rely on that and execute that Julia code and pass in, for example, the model to it to run. And you can do this for parameter sweeps and linearization and so on. In fact, I think it's the next slide, if I'm not mistaken. No, here's one example, auto tuning of a PID controller. So this is something that we've actually done, and this is the result of that. You can define an auto tuning analysis where you specify a bunch of things like a model and then a bunch of parameters around the auto tuning exercise, and then it will spit out basically a tuned PID controller for your system. Okay, and this is something that any user could implement on their own. We've implemented it, but we don't have any special powers that users don't. So here's a set of current and planned analyses that we want to be able to do: transient analysis, steady state analysis, PID auto-tuning, linearization, modal analysis, doing parameter sweeps, potentially over multiple parameters, design optimization, surrogate generation or reduced order model generation, model calibration. The point here is that you can you first start by building the models that represent your system. Then you can create whatever analyses you need with Julia to analyze those systems. Obviously leveraging the things that we are going to provide as part of our platform, but having the freedom to implement things that are very specific to your particular product and in your particular workflow. So there's a simple API for doing this, for adding new analysis types, and they will allow you to get access to the symbolic representation of one or more models that you want to associate with the analysis. Once they're added, these analyses can be manipulated in the GUI. You can actually bring up dialogues and change parameters and store them in your libraries and all of that stuff. There's essentially a graphical representation for them. And the analyses can produce multiple artifacts. And so in our on our JuliaHub platform, we have the ability to run these analyses, and then the artifacts that are generated can be managed on our platform. And they can be parameterized, as I mentioned before, so that you can then, even within the GUI, run an analysis and then turn a knob and run the analysis again. And you can use extends to kind of functionality inheritance to allow you to create variations of these analyses for different purposes or scenarios or whatever. And all the while, of course, you have access to the full Julia environment, which means that these analyses, once you have the analyses, they are effectively just functions in Julia. And you can then jump into Julia and you can call the functions, you can do plotting, you can do scripting, you can interact with notebooks, because again, it's just Julia at that level. And we have just-in-time compilation of everything. What Julia is really giving you here is this expressiveness of a high-level language that then compiles down into machine code in a just-in-time fashion so that you get the speed of C. So all of that is in play here. And this really gives you just infinite possibilities for building on top of this. What Dyad is really trying to do is it's trying to take really common patterns for developing models of systems and make that part easy. But then by generating essentially software from that, you can then build more complex software systems out of that. So conclusions here. First, the Dyad really, it's in the name. We're really trying to balance the hardware-oriented and software-oriented requirements that modern products have. Okay, so that's part of our vision for these things. A lot of what we're doing is looking at what works and trying to hold on to that, and trying, things like symbolic manipulation is very effective. We want to do that, but how do we then use that in conjunction with things like AI or GPUs or whatever the current technologies are? We acknowledge that engineering workflows don't just stop with building the model, right? We have to think about, what are you going to do with the model? What questions are you going to ask? And what kind of answers do you want? And what do you want to do with those answers? How do you want to manage those answers? And there are a bunch of learning resources. So you should investigate this. This help.juliahub.com/dyad/dev. There's a bunch of documentation that we have online now about the Dyad language and how to install Dyad Studio and so on. And I want to emphasize that you're really gaining the power and speed of Julia everywhere in all of this, because even though we have this Dyad language for at a high level describing problems, ultimately it all compiles down into Julia. And I should mention that JuliaHub tools are free for academic use. So if you're in academia, you can contact us about that. And our plan is for the Dyad platform itself to make nearly everything available via a source available license, so that people will have access to that. It's not open source, but it's sort of the next best thing. And so with that, I covered all the topics I wanted to introduce. I would encourage people to go out and take a look at Dyad Studio. If you download the extension, there's a link in there to getting started. There's quite a bit of documentation that you can go through to look at about how to use the extension and what you can do with the language and some of the standard libraries that are already available. And there'll be a bunch more stuff coming as we crank that out. So this is, as I've mentioned a couple of times, just really the tip of the iceberg. It's just us getting started. So with that, I didn't monitor any of the questions. So was there anything, Ranjan, you want to flag that wasn't answered during the presentation?
Yes. So firstly, thanks, Mike, for the presentation. Before I start sort of flagging certain questions, I just wanted to let the audience know that at JuliaHub, we do a version of this presentation along with a hands-on demo and workshop at each company, right? So if you're from a particular organization and you'd like for us to do a version of this workshop at your organization, please get in touch with us at sales@juliahub.com, or you could go to our website and just fill in the contact form, and we're happy to help you there. So, having said that, I think there are a couple of questions. Firstly, a couple of comments that got sent to us directly. So is there an equivalent of Modelica.media within the Dyad ecosystem? Because this is the first question.
Yeah, so there isn't at the moment, but we actually have a talk at JuliaCon where we'll be talking about that. So I expect there to be one fairly soon. And so that is something that is actively under development right now. And JuliaCon, for those who don't know, it's going to be in Pittsburgh this year. It's at the end of July. So if you're interested in these topics, we would encourage people to come to JuliaCon. We're going to be there, and we're going to be talking about Dyad at JuliaCon as well. So stay tuned. The answer to that one.
So there was one question about will a recording of this be made available for colleagues who could not attend? Yes, we will follow up with a recording of this presentation. It's essentially an unlisted YouTube link, and you should feel free to forward this to your colleagues. The next question I wanted to flag was, does Dyad still build on top of JuliaSim compiler, or is everything now moved to the modeling toolkit compiler? Any comments on that, Mike?
Dyad is meant to be sort of agnostic to the particular backend. That was actually part of the reason to do it, was that we wanted something that focused just on the modeling part and not the details of how do you like declare symbols and how do you specify, equations and all of that stuff. We wanted to, because that's a little bit dependent on what the backend would be. So at the moment, it depends on modeling toolkit. I don't. We're actually working on sort of the successor to JuliaSim compiler internally, and it may be that we ultimately end up depending on that. I'm not quite sure how that's all going to play out. I mean, that is kind of the plan, but for the moment, at least right now, it's largely targeting modeling toolkit as the backend.
Yep. Thank you. Feel free to post questions in the Q&A or in the chat, folks. So maybe one thing we could highlight there is how do people get started using the language or using the software, Mike? Is there a getting started page that they could take a look at and so on? Do you want to walk through a little bit of that?
Probably the best way to do that, let me try and change desktops here, change windows here. Just a sec. I'm going to share a different window and we can maybe hopefully get that working. Now, if I could just find the share button again. Where did it go? There it is. Okay. Let me see if I can share this. I think I can. Yes. So hopefully you can see this. This is just Visual Studio Code. I hope that's visible. Correct?
Yes, we can see it.
Yeah, okay. And so if you just go to the extensions tab and you click on, you type Dyad, fortunately, we are the only Dyad in town. So you won't have any trouble finding us here. Don't tell anybody to use that name. I don't want it cluttered. I like the fact that we're the only one. And you can then install that and you can see like what the latest version is and so on. If you look in here, there's a quick start guide. You can see at the very end of this, there's a quick start guide. You can just, that's one link you can follow, okay? And that's going to open up a separate web browser, which you actually won't be able to see because I'm only sharing my VS Code thing. But you can see in here, it's got a couple other links in here to things you can do. But basically, this is where I would start. And then once you're done, sort of with some of the prerequisites, just go to the Getting Started guide and jump in. And so what you should see, I mean, I can click on this and then I'll share, I guess, the browser when I do that. I'll go back to sharing the browser and then I'll show you some of the documentation, I guess. Just a sec. We'll try and share this again. Where are we now? Getting started. Is this it? Yeah, this is it. Share. So that takes you to a page like this. There's actually a page on the installation. I assume you guys can all see this. Yeah, you can. There's installation, there's getting started, which walks you through some basic stuff in terms of getting things running. When you create a new library in Dyad, it actually builds a model with some test cases and an analysis out of the box, so you can do something right away with it. But you'll notice down here, there's like the standard libraries, there's just a ton of documentation on the different types of analyses that are available. There's a bunch of documentation on the different standard libraries that are out there right now. We have block components, rotational components, translation components. And click on these and go through and look at the documentation for any one of these things, right? And again, there's a lot more to come. This is just sort of us getting started, but there's a fair amount of documentation in here. And there's actually some more detailed tutorials on, for example, doing acausal modeling in Dyad, how that's actually done, walks through an example of building an RLC circuit and an analysis of that RLC circuit and running simulations. So but there'll be, as I said, a lot more to come, but this should be pretty good for getting started.
Yes. So another question I see in the chat is, so what exactly is the main contribution of something like Dyad over Modeling Toolkit? So I mean, Modeling Toolkit's open source and people can use it today already. So why Dyad and when Modeling Toolkit already exists?
Yeah, so there's a couple things there. One is that modeling toolkit's fairly low level. We have this notion of what we call the Turing tar pit. When you get into just a programming language in general, you can do all kinds of things. So it's very powerful, but it becomes very difficult to reason about it. Dyad is a sort of more strict approach to this than Modeling Toolkit. It has this notion of units and checking and a bunch of correctness things that it tries to do that that Modeling Toolkit can kind of do, but because of the dynamic nature of Julia and Modeling Toolkit, it kind of has to defer that until you actually try and run your problem or do the symbolic, manipulation. And Dyad's really trying to do that up front. It's really trying to keep you sort of on a track that isn't going to lead to the Turing tar pit, let's say, where you can no longer reason about your system. So things like building things graphically is a good example, right? So you can build all kinds of Modeling Toolkit models, but the thing is, how would you represent them graphically? How would you build deep hierarchies of them and compose them graphically and drag them and connect them and so on? So there isn't really a capability in Modeling Toolkit for doing that, largely because it doesn't have, for example, the same kind of metadata-based approach. But also one of the things that Dyad does is Dyad itself, the core kernel and the builder and things, they run essentially in a browser. So they, separate from the sort of the Julia runtime. And so that means they can run natively in a browser, and you can compose systems with very quick feedback directly in a browser without having to sort of communicate with some remote server all the time for every little operation, right? They can do that right in their own process space in the browser or in VS Code or in Electron. So that's another difference just from a software architecture standpoint, is that it runs natively in a browser. But ultimately, it all does compile down into Julia. But it's really trying to make it so that the process of building models is one that's intuitive and pleasant and full of constructive feedback, immediate constructive feedback. But nothing prevents you from dropping down into Julia and writing models in Modeling Toolkit. We're just trying to take it's a sort of trying to take any boilerplate or friction out of that process, in part by doing it at the Dyad level.
Yeah, and there's also the one-to-one sort of, maybe you already mentioned this before, Mike, but there's also the one-to-one bidirectionality with our graphics that where you make an update to the code and it affects immediately on the graphical, because on the graphical side, because this runs in the browser, that's possible.
Yep. And so yeah, the point is that there's one representation of your models in the core, but you can look at it as a textual representation or as a graphical representation. And so you can make changes to one and it'll automatically influence the other. So that's another thing that concept isn't really there in Modeling Toolkit itself, because it focuses just really on the math and the symbolic representation, and not on the sort of higher level model representation.
Right. So the next question I have is on media type propagation. So if there can be sort of reverse flows resulting in varying chemical components within the streams, how are these media types propagated? Maybe I'll repeat that question. How are media types propagated if there can be reverse flows resulting in varying chemical components within the streams?
They really aren't. So what you'd really need to do in that case is you would need to, oftentimes when you deal with something that has multiple components in it, you have to identify upfront, there are n components in this fluid, right? And so the way I would approach a problem like that is I would figure out what's the total set of components that you have to worry about, whether it's backward or forward. Then create your media properties in such a way that you take all of them into account. So if I have X mass fraction of this and Y mass fraction of that and so on, what is the density of it? And then bidirectional flow doesn't introduce any changes in media. It's not like it's a different media, whether it's flowing backward or forward. Now we do have the same stream connector or stream variable on connectors concept that Modelica has. We have some of the same operators that Modelica has for querying about what's actually in the stream as it's flowing past the connectors. So the key thing is that the path variable thing is independent of direction. If you have a flow path, everything's in that flow path, okay? Whether it's flowing forward or backward, everything's still in that flow path. And so everything has the same medium in that entire flow path. Then you'd use the stream concept to handle, for example, the fact that if it's flowing one way or the other, that you have, convection of this stuff one way or the other. And then finally, like I said, you'd use components in the media model to represent all the different constituents that could be in there. And maybe, you have, like when you have backflows, you're taking stuff from upstream and pumping it back downstream. But the idea is they're mixing then. So you really have to take into account having everything present in your medium model. And then I think everything would work out pretty cleanly. But they're just separate concepts. Path is separate from stream, is separate from components or constituents, however you want to look at it.
Well, thanks. There was one question about pricing, and maybe I could sort of generally comment on, just our pricing model. We have two different kinds of pricing based on whether you just want to use the Studio VS Code extension, or if you also wanted to use Dyad Builder, which is our graphical interface where you can drag and drop components and so on. So please do contact us at sales@juliahub.com, and we can generate a quote for you. And of course, it'll have different pricing components that we can sort of show you and explain to you in detail. So thanks for asking that question. I believe there's a follow-up question to the reverse flows question here. I believe the sort of suggestion is that the approach you described results in huge vectors of components on a flow sheet. Just sort of curious how you would handle that type of scenario, Mike.
Yeah, I mean, I'd have to see the actual system to understand to what extent you could contain this. I mean, there must be some conventions that are being followed here that about how far back something could backflow, for example. Otherwise, I'm not quite sure how you can avoid the mixing of all these components. So
Right.
I'd have to actually, I'm not sure I can answer it without actually looking at something in detail, and maybe a different approach would be needed, but without the details, it's hard to speculate.
Yeah, so please do get in touch with us and we can take a look at your model. Mike, do you want to generally comment on how you would do flow sheeting within Dyad itself?
Yeah, I don't know. I'm not sure. I'm not sure I have off the top of my head. I'm not sure I have anything really to add there. I think there's actually other people within the company like Avinash who would probably be better at answering a question like that anyway. So I think the best bet is just to reach out to us and we can talk in terms of a concrete example.
Yes, absolutely. We can certainly get you connected with the right people. Let us see. Well, I don't see any more questions in the chat or in the Q&A. I actually do see one last comment here, which is on it would be nice to handle large-scale thermofluid models in Dyad. And so I know, of course, like in Modelica, of course, there are lots of really complex thermofluid models that end up being really stiff. Is there anything that Dyad can do here to show some kind of differentiation? Any comments there, Mike?
For sure. I mean, I think, for example, Modelica, they have this homotopy operator. I think that we have plans internally to be able to try and essentially automatically identify from the structural problem things that we might be able to do to make the solving of the nonlinear systems, more likely to converge. For example, I'm not the person to ask there. Chris Rakakis is the person to ask there, but I've had discussions with Chris about that. So being able to look at the mathematical structure and perform some sort of symbolic analysis of the system and find out what is the best way to approach this to be able to solve it. Because in these sorts of, especially when you get into things like two-phase flow and stuff like that, you get some really vicious nonlinearities and stiffness. And a lot of times just getting the solutions to converge is really quite a challenge. And so I think we have actually quite a few ideas on how to do that in a practical sense using the various libraries that we have underneath the surface. We have quite a wide range of solvers. I didn't point that out, but there's a whole range of nonlinear solvers and a huge collection of essentially differential equation solvers that we have under the hood that are essentially suited for different purposes. And so that's also an advantage that we have. It's not a sort of one size fits all thing where we're just trying to do everything with something like DASL. And in fact, Chris and I were recently having a discussion about the fact that for fluid systems in particular, he felt that explicit solvers were in general going to perform better than the implicit solvers, but implicit solvers tend to be sort of the default in the Modelica world. And I think we have a much bigger set of implicit solvers with, like I said, varying capabilities, specialized to different kinds of problems that we can bring to bear on fluid systems, for example. But I also think that just in general, the way that we approach the technical computing side, we have within the Julia world, we just have such a rich set of solvers that I think we should be able to do quite well on some of these fluid problems. This combination of good solvers with symbolic information and being able to sort of analyze the structure symbolically and gain some insights from looking at that structure that make it so that we're more likely to converge on a solution. I think all that's quite reasonable in our platform.
Yes, and there was one other question about can you use something like Clapeyron.jl within the flow sheeting applications, and the answer is yes. And we should take a look at how exactly what type of integration works best for your use case. Let's see, there's another question here. Would Dyad have the capability to export or translate models built on top of Dyad into base non-proprietary Julia code?
I'm not quite sure I understand the question. Is it to make
Yeah,
it's obfuscated in some way so that people can't actually see the Julia code? I'm not quite sure what the goal there is.
yeah, I'm not quite sure either. So if we are also yeah, if you could get in touch with us, we can we can figure it out together. I mean, in general, Dyad the Dyad kernel will generate Julia code, and
Yeah,
of
and in
course,
fact, it can generate obfuscated code as well. We have various tools for taking that Julia code and obfuscating it. So
yes,
we aren't actually leveraging that, but as I alluded to at the very beginning, I think we architected this to protect for a lot of important contingencies, and that was one of them. How do you actually distribute the resulting code in such a way that it can't be easily reverse engineered? And I think we have a a plan there that we could share with people. It isn't implemented, but we feel like there's nothing standing in our way except just the implementation effort. Architecturally, it should work just fine.
okay. One more question on licensing. If a company has a fixed number of developers but more users, but want to retain scripting capabilities within Julia for workflows, I guess this question is incomplete. If you don't mind, actually, if you don't mind getting in touch with a question on that, if you have more questions on licensing and so on, we're happy to we're happy to answer, and in fact get on a call and of course explain to you our various components.
Yeah.
Yeah, any other final comments? I think that's it from questions. Please do get in touch if you have more questions, by the way. It's sales@juliahub.com. And we're happy to help. Any other final comments, Mike?
Nothing from me. I just hope that people go out and kick the tires on this and check it out and give us some feedback on it. We're really trying to build a platform for the future, and we want it to suit people's needs. So
Yes, and I would like to strongly echo that as well. Thank you, everybody, for your time and attention today, and do give this tool a try and let us know. Sanjeev, any other final comments from your end?
Yep, we would be posting the record session on our website in a couple of days' time, and we would also reach out to you with an email, and you'll have the link to the record version of this webinar. In case you need any further information, you can reach out to us on the same email, and we shall get back to you at the earliest.
okay.
Thanks a lot. Thank you, everyone. Have a great
Thanks,
day.
everyone.